Well, welcome back to our lecture videos. We're now starting chapter 6, section 6.1, ideals and quotient rings, and 6.1 is on ideals and congruence. So remember that in the integers z, for a and b, the elements of z, such that a is congruent to b mod 4. We're going all the way back to chapter 2 again. This meant that a minus b is a multiple of 4. 4 divides a minus b, which means a minus b is a multiple of 4. So if I let I be equal to all the integers that are multiples of 4, that'll be 0, plus or minus 4, plus or minus 8, plus or minus 12, plus or minus dot, dot, dot. Then the congruence modulo 4 may be defined as a is congruent to b mod 4 if and only if a minus b is an element of this set here, I. So, note that I is a subring of the integers. It's the multiples of 4. Furthermore, they produce the product of any integer, and the multiple of 4 is itself a multiple of 4. So, multiples of 4 times any integer is always going to be a multiple of 4. I mean, 3 times a multiple of 4 will still be divisible by 4. It's going to be a multiple of 4. So thus, the subring I has the property that whenever k is an integer and I is an element of big I, then k times I is in big I. So it's a little bit stronger than just closure. The fact is, you take any integer, multiply it times I, you'll be back inside of I. So we defined a subring I of a ring R is an ideal, provided that whenever R is an element of R and A is an element of I, then R times A is an I and A times R is an I. So an ideal is a subring with a very special property. And it's this property in this example we were just talking about. It's the idea of just one element is inside your set, I. You take any element inside the ring, and yet the product, A times R is an I, and, because you may not have commutativity, R times A is an I. So R times A is an I, A times R is an I. You've got to check both ways. So this is an ideal, and it's a little bit stronger than just being a subring. Subring, you remember from your Theorem 3.6, you've got to have closure under subtraction and closure under multiplication. Well, we're focusing on this multiplication. It's stronger than just closure. One element is inside the set, and the other element is any element inside the ring, and their product will be back inside the set. So, in our previous example of the integers, and I is the multiples of 4 in Z, I is actually an ideal in Z. Another example would be this. You got the integers again, and the integers is a subring of the rationals. The rationals are all the rational fractional numbers here, integer divided by an integer. But, let me give you an example. 3/8 is clearly a rational number, and 4 is clearly an integer again. But watch this. What is 3/8 times 4? Well, 3/8 times 4 is actually 3/2, and 3/2 is not an integer. So here is a product of one element inside my set, another element inside the ring, but their product is not back inside the set. So therefore, Z is not an ideal of the rationals. So the integers are not an ideal, right? It is a subring, clearly, but it is not an ideal. So these ideals are actually quite special with this idea of one element inside the set times an element inside the ring. Their product is supposed to be back inside the set. So, as you have to check the R element of the ring R and A element of the set I, with A times R is element of I and R times A is an element of I. You've got to check both ways, R times A and A times R. If you do not have a commutative ring, you may have this scenario. R times A is an element of I, but A times R is an element of I. Then I could call this ring an ideal, a right ideal. Now, I could be called a right ideal, and that's a fancy term for it. In math, we're always looking for fancy terms. but by definition, it is not an ideal. Not an ideal of R. You gotta be two-sided. Ideals have to be two-sided ideals. You gotta multiply on the left and multiply on the right. This is multiplying the element on the right. This is multiplying the element on the left. They both have to be inside of I to be called an ideal. So here comes your next favorite theorem. That is Theorem 6.1. Theorem 6.1 says this: a non-empty subset I of a ring R is an ideal if and only if it has these properties. 1. If A and B are elements of I, then A minus B is an element of I. And 2. If R is an element of the ring R and A is an element of I, then R times A is an I and A times R is an I. Now if you look at this guy, this looks awfully familiar. It should look very similar to Theorem 3.6 on proving subrings, but it's been adjusted ever so slightly. So part number 1 is your closure under subtraction, but part number 2 is actually one element inside the ring, one element inside my set, and it's the definition of ideal. That product, and check both ways, has to be back inside the set. And it's got to also be non-empty. So if I really analyze this theorem from theorems in the past, mainly Theorem 3.6, we have this idea. It says this: so by Theorem 3.6, by Theorem 6.1, what do we need to show? So because of that non-empty aspect, we got to show it's non-empty, and the easiest thing to show non-empty is you got to show the zero element from ring R is inside of I. The second thing, you got to show the classic closure under subtraction. You're going to give yourself two elements inside your set and whatever property that means, and then you're going to show that the subtraction of those two elements must also have those properties, aka be inside the set. And then you got the definition part of ideal. It's stronger than closure under multiplication. It's that part that if you give yourself an element, arbitrary element inside the ring, and you give yourself one of those elements up here, just one of them, A, inside of I with all its properties, then I'm going to show R times A is an I, and I have to show A times R is an I. Now, if I happen to have a commutative ring, they're equal to each other. That's why we love commutative rings. Then all I have to do is show up one time and state the fact that it's commutative and be done with it. But if it's not a commutative ring, I got to show both sides. Then we can say by Theorem 6.1 that I is an ideal of R. Note the connection to Theorem 3.6 is what I've been trying to emphasize here. So there are actually three things to show if you want to show a set I is an ideal of a ring R. So, definition up here. An ideal generated by a single element from R is called a principal ideal. So, here we go. Theorem 6.2. Let R be a commutative ring, with identity, and let C be an element of R. This is my classic fixed element, with I being all the multiples of C and R. Just rewriting it in set notation. That is, I is equal to the set R times C. C is fixed, such that R came from R. So it's the multiples of C, where C was fixed. Then I is an ideal of R. In this case, I is the principal ideal, quote, generated by C, and another notation for that would be I is equal to a little round bracket, C, and close round bracket. That's my little standard notation for a principal generated by C. This is an ideal, principal ideal generated by C. So let's prove this thing. All right, so if I want to prove an ideal, I'm going to quote my new favorite theorem, 6.1. I got your three things: non-empty, closure under subtraction, and I'm going to let myself have an arbitrary element in R and an element inside the ideal, and I got to show that product is back inside the ideal. So this is very, very similar to what I did when I was proving subrings. So let's do it again. And so first thing I got to do is I got to show it's non-empty. Well, I'll start with your givens. Given R is a commutative ring with identity, and C element of R is a fixed element of R. Well, as R is a ring, then 0 in R is an element of R. Definition of ring, you've got to have a 0 element, okay? Then, and as 0 in R times C, that's going to be the same thing as C times 0 in R, which is equal to 0 in R. Hence, 0 in R is an element of I, and I is non-empty. Now remember, we're trying to show I is an ideal. I got to show it's non-empty. So I's are all the multiples of C. Well, since 0 times C actually equals 0, but 0 is a multiple of C, that puts 0 inside of I. And that makes I non-empty. So first part, usually the 0 part, showing it's non-empty, is usually the trivial part. So let's continue on. Now I'm going to show closure under subtraction. So to show closure under subtraction, I'm going to give myself two elements, just like I did with subrings. So I'm going to let my favorite two guys, let x and y be an element of I. The thing I'm trying to show is an ideal. Therefore, there exists, great time for subscripts, an R1 and an R2 element of R, such that, we have to have that look, such that x is equal to R1 times C and y is equal to R2 times C. That's what you look like to be inside of I. You look like R times some, the C element. C is fixed. So R1 times C and R2 times C. Okay? Well, since x minus y is equal to R1 times C minus R2 times C by substitution, then x minus y is equal to R1 minus R2 times C by factoring. And the fancy word is it's the distributive property. Okay. Well, as R1 and R2 are elements of ring R, then R1 minus R2 is an element of R because R is a ring. Hence, x minus y is an element of I. Now again, from that structure of being an I, y is x minus y and I, it has a structure that looks like somebody times C, where that somebody came from R. X minus y is equal to somebody times C, where that somebody came from R. That's what I'm looking for to be inside of I, and x minus y has it. Now, the third part is the new part. So part one, showing it's non-empty, part two, showing closure or subtraction, is exactly the same thing that we did when it came to subrings. So, the third part, subtle difference. You give yourself one element, and I'm going to use x. As x is an element of I, then there exists an R1 element of I such that x was equal to R1 times C. Just my same setup, but only using one guy. And now I need to give myself an arbitrary element inside of R. Well, what's the obvious element that should be inside of a big R? Well, a little r without a subscript, so it'll be a different guy. be an element of big R. Very arbitrary here. Then X times R is equal to R1 times C times R by substitution. Thus, X times R is equal to R1 times C times R by associative property. This gives us X times R is equal to R1 times R times C by commutativity. And typically I don't have a commutative property, commutative ring R. But in this one, I was given that R was a commutative ring with identity. So I just needed the commutative ring Y there. So C times R is equal to R times C. Hence, X times R is equal to R1 times R times C by the associative property. Now let's finish it up. Well, as R1 and R are elements of R, then R1 times R is an element of R because R is a ring. Thus, X times R is an element of I. So I've got X times R is an element of I. But because I have a commutative ring, that just, I don't have to redo this entire statement again. But if I didn't have a commutative ring, I actually would. I have to reverse order. But because it's a commutative ring, and as R is a commutative ring, then R times X, which is equal to X times R, is an element of I. So I've got both of them element of I. Therefore, by theorem 6.1, I is an ideal of R. You're not just an ideal, you got to tell me what the big ring is. And I'm done. So here's my proof of the fact is that principal ideals, an ideal generated by one element, which is in this case the C element, is an ideal of R. And again, looking at all the fine points here. So we have here that X is an element of I, and R1 is an element, there exists an R1 element of I such that X is equal to R1 times C. And I gave myself an arbitrary element, plain R is an element of R. And things I tried to show was, number one, X times R is equal to somebody times C, where that somebody came from R. That was satisfied here, and also the fact that I had a commutative ring that also gave me, since X times R is an I, R times X I get for free is going to be an I. And so with all three parts, I end up getting that I is an ideal of R. So it's more subring stuff with a subtle difference right here under the multiplication aspect of this thing. Section, or theorem 6.3 says this. Okay. Let R be a commutative ring with identity, and C1, C2, out to Cn be an element of R. Then the set I, which is equal to R1 times C1 plus R2 times C2 plus R3 times C3 plus plus Rn times Cn, such that R1, R2, R3, Rn are elements of R, is an ideal of R. In the last theorem, we talked about a principal ideal, ideal generated by one element. This guy is called a finitely generated ideal. So instead of generating by one element, we have n elements that are all fixed. These are my fixed elements. I'll put the word fixed right above that. These guys are fixed, the C1s through the Cn's. And see the linear combinations thereof of the multiples of the C1s through Cn's still will form an ideal. So it's pretty much just like the proof of Theorem 6.2, except we got the multiple terms on here. This is, again, definition. And it's the same kind of in Theorem 3.6, I was called a finitely generated. Well, we actually use it in Theorem by Theorem 6.2 and 6.1, so I'll just quote it as 6.1. Theorem 6.1, I is called a finitely generated ideal generated by C1, C2, dot, dot, dot. And the little symbol for that is I would be equal to C1, comma, C2, comma, dot, 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 up to Cn with little round brackets around it. That's called a finitely generated ideal. So there's a finite number of fixed elements that you're generating the ideal out of. Okay, all right, so here's the big question. Once you have an ideal, I, in a ring, well, what's next? What can you do with this stuff? Well, the next one is going to be another definition. So lots of definitions in chapter 6 here. Let I be an ideal in a ring R, and let A and B be elements of R. Then A is congruent to B modulo I, written A is congruent to B mod I, provided that A minus B is an element of I. Now you're going to have to break the habit because we've done so much modulo stuff with modding out by n and modding out by p of x, polynomials. You got the idea of divides. You know, remember from the integers, A is going to be mod n meant that n divided by A minus B. A of x is going to B of x mod P of x meant that P of x divides A of x minus B of x. That divides concept, not anymore. Now, A is going to B mod I means that A minus B is an element of I. Now, A and B may not be elements of the ideal, but the difference, their difference is going to be an element of I. So, an example of something like this, remember we talked about the multiples of 4 in the previous examples I gave you guys. Now, 1 and 5 are not multiples of 4, so they're not 9. But 1 minus 5, which is negative 4, is a multiple of 4, so even though 1 and 5 are not 9, their difference is an I. So 1 would be congruent to 5 mod ideal generated by 4. There you go. So this idea of the difference between two elements is still inside your ideal. So we have theorem, and you say, again, catch a pattern on this stuff, because that's what modern/abstract algebra is all about. Theorem 6.4 says this: let I be an ideal of a ring R. Then the relation of congruence modulo I is 1, it's reflexive, 2, symmetric, and 3, transitive. It's going to create equivalence classes. And then if I got equivalence classes and I can somehow figure out a way of adding and multiplying, I can create new rings out of this thing. So with these ideals, I can create new rings. So here's the deal, reflexive. You're always congruent to yourself. So A is congruent to A mod I for every A. Now why is that? Well, A is congruent to A mod I means that A minus A is an element of I. A minus A is the 0 element in your ring, wherever you came from. And you remember our theorem 6.1, first thing, it's got to be non-empty, which meant that it's a subring, which means that the 0 element's got to be inside of I, because I is a subring with this extra property. So never forget, I is a subring with extra properties, and I'll explain the importance of the extra properties and what's going on here. Symmetry. If A is congruent to B mod I, then B's got to be congruent to A mod I. If you're congruent to somebody else, somebody's got to be congruent right back to you. And again, the idea is this. If A is congruent to B mod I, means that A minus B is an element of I. I, again, is a subring with extra properties making it an ideal, but it is also a subring. And being a subring, if A minus B is an element of I, Then the additive inverse, -1 times, if you happen to have a ring with identity, or just the additive inverse, negative of the element. Negative a minus b is actually negative a plus b, which is the same thing as b minus a. B minus a is the element of I, which means by definition, b is congruent to a mod I. So if you're congruent to somebody, somebody's got to be congruent right back to you. Then, of course, the transitive property. If A is an element of, A is congruent to B mod I, and B is congruent to C mod I, then A's got to be congruent to C mod I. Well, let's still go through the definition. If A is congruent to B mod I, by definition, congruence modulo I means that A minus B is an element of I. If B is congruent to C mod I, means that B minus C is an element of I. So I've got two elements of I, A minus B and B minus C. Now, I is an ideal. Keep focusing on that. So if I add these two suckers together, A minus B plus B minus C, minus B plus B cancels, so I get A minus C. It's still got to be an element of I, which means that A is congruent to C mod I. So we got reflexive, we got symmetric, and we got transitive properties here with our new congruence modulo an ideal. So theorem 6.5 picks it up there and says this, quote, let I be an ideal of a ring R. If A is congruent to B mod I and C is congruent to D mod I for some A, B, C, and D elements of R, some ring R, then A plus C is congruent to B plus D mod I, and A times C is congruent to B times D mod I. What is this theorem telling us? Well, if you go back and look at the stuff that we've done before, it's a similar pattern. We're trying to define the idea that you can add these congruence classes and you can multiply these congruence classes. And because you can add them and multiply them, we're going to come up with a new notation for this congruence class concept here. So the notation, we will denote the congruence class modulo I with A plus I. It's going to be called a coset. We'll get there in a second. So we have theorem 6.6 that says this. Let I be an ideal in a ring R, and A and C be elements of ring R. Then A is congruent to C mod I if and only if A plus I is equal to C plus I. So this congruence is going to set up two congruence classes. If A is congruent to C mod I, then A plus I notation will be equal to the C plus I notation. And the congruence class A plus I is called the coset, and because we put the A on the left side, it will be called a left coset. There is something we can talk about. A right coset would be I plus A, okay? But when it comes to rings, because addition is commutative regardless of the type of ring you got, we don't typically talk about it being left or right cosets. We just talk about a coset. Now, in chapter 7, they start talking about group theory. And in group theory, they will distinguish a new concept of a group, but they will go back and look at cosets again and define the left and right, and they will be somewhat different. So, corollary 6.7 says this. Let I be an ideal in a ring R, then two cosets of I are either disjoint or identical. So these cosets are basically, they are taking the entire ring and putting them into categories. That's what these congruence classes do for you. They put them into categories, and the categories will be called A plus I, B plus I, C plus I, so forth and so on. So this is how the elements look. Now, you remember way back when we were doing congruence classes, Z mod N, in Z mod N, the congruence classes look like pointy brackets with, some number in there like a P or something like that. When we looked at F joined X modded out by P of X, then those congruence classes look like pointy brackets with a polynomial inside of them. We used the pointy bracket notation. Well, okay, with congruence modulo and ideal, we're dropping the pointy bracket notation and we're putting the element plus I. The plus I lets you know that you're dealing with a congruence class and not just an element in ring R. So, Now, this is section 6.1. 6.2 is going to dive a little bit deeper into these congruence classes as well as subrings. And I'll pick that up on the next video.